Today we're going to be working through 1.6, position, velocity, and acceleration. And I'm assuming many of you have taken physics. You have talked about the relationship between position, velocity, and acceleration. So we're going to just briefly recap that and talk about how it specifically applies in calculus. So position is exactly what it sounds like. It's the location of an object at a particular moment t. Typically, you're going to see that represented as s of t, x of t, or y of t. So it's defined as a function. And then thinking about what the velocity is the rate of change of the position, which means that the velocity, by definition, is the derivative of the position. So you're going to see velocity represented as v of t, which is basically just taking the first derivative of the position function. Note that velocity has a sign element, meaning if it's positive, it's going to be moving to the right or up, depending on what type of motion, if we're talking about vertical motion or horizontal motion. And it's going to be negative if it's moving left or down, again, depending on what type of motion we're talking about. And then if the velocity is 0, then the particle is not moving at all. So we would say that it is at rest. And then acceleration is the rate of change of the velocity. Therefore, since slope is rate of change, since derivative is finding those slopes of those tangent lines, the acceleration is a of t, which is defined as the first derivative of velocity, or the second derivative, since we talked about higher order derivatives, the second derivative of the position function. So initial position you'll often see represented as s naught, and that's the position at time 0. Similarly, you'll often see v naught used for the starting velocity or the velocity when t equals 0. Speed is defined to be the absolute value of the velocity. So, for example, if you think about driving a car, if you're looking at your odometer, the portion that measures speed in the car, there are no negative speed values. You're talking about how fast you're moving, whether that is the speed of slowing down or increasing in velocity. So speed is the absolute value of velocity. So it's always positive because we're talking about how fast, not which direction. Direction is not relevant. And then displacement and total distance, these two very often get confused. Displacement is talking about the overall net change, meaning if I'm at my house and I go for a walk around the block and I end up back at my house, my displacement would be 0. Versus the total distance would be the actual amount that I traveled. So usually when I go for a walk, it's about a 1 mile walk. So my total distance traveled would be 1 mile versus my total displacement would be nothing, because from the time I left to the time I got back, I'm in the same position. So displacement is that net change, the final minus the original. Total distance takes into account if you were moving left, right, if you were retracing your steps, all of that is taken into account. Okay, so for example 1, we're just going to find the velocity and acceleration functions based on the given position function. So to find the velocity function is the derivative of the position function, and we can just apply the power rule here. That's going to give us 3t squared plus 1. To find the acceleration vector, we're going to take either the second derivative of the first derivative of the velocity vector or the second derivative of the position vector. Either way, we're going to use the power rule on this 3t squared plus 1, and that's just going to give us 6t. Okay, for these examples 2 through 10, we're going to be using the position function that's given up top. And it's giving us an object moving along a horizontal line. So moving left or right. Something to be cautious of when you're doing these problems, the actual math that's happening is incredibly easy, but you really need to take your time when you're reading through the questions to make sure you're actually answering the question that is being asked. Sometimes we rush through the things that seem to be easy and then we mix up displacement and distance, or we just aren't paying attention to a simple detail and then lose points off of that. So just make sure you're paying attention to the directions. So question 2 says, what is the initial position of the object? Meaning, where is the object when the time is 0? Well, when the time is 0, that position is 24, and it says our distance is in feet. Don't forget your units. Question 3 asks for the velocity of the object at 1 second. The first thing we need to do is find the velocity function, which is going to be 3 times 16, 48, just using the power rule. T squared minus 36 times 2, 72 t. And then I'm going to evaluate that function when t is equal to 1, so 48 minus 72, which is negative 24 feet per second. Again, don't forget your units. I do want to see that you found the velocity function as a function in terms of time before you actually take the step to substitute in the 1 value. I want to see both of those pieces of information. Number 4 is asking you for the speed of the object. Now, speed is not talking about acceleration, so that's not what this question is asking you. It's asking you to take the absolute value of the velocity vector, which is, I should say, the velocity vector evaluated at 1, which is 24 feet per second. So thinking about the difference between 3 and 4, 3 is telling us that at 1 second, the object is moving 24 feet per second to the left, since it's moving horizontally. It's moving at that speed. It's moving at that velocity. 4 is just asking us how fast is it moving, not what direction is it moving. Velocity gives us the speed and the direction. 4, the speed is just asking us how fast is it moving. It's moving 24 feet per second. So that's the big difference between those two. 5 is asking us for the acceleration at 1 second. So again, the very first thing that I'm going to need to do is find the acceleration function. So I'm going to take the derivative of this velocity function, 48 times 2, 96t. I'm just using the power rule, minus 72. And then I'm going to find the acceleration when t is 1, which is 96 minus 72, which is also 24, but now feet per second squared. Since acceleration is the derivative, that is how this is changing. The derivative with respect to time, so we're sort of, you can think about the units. The units are also using the power rule. 6 is asking at what time is the object at rest. At rest is telling me, or it's asking me, when is the velocity vector equal to 0? So what I'm going to do is I'm going to set up the velocity function. I'm going to set it equal to 0. That's just a quadratic that you're going to solve using any Algebra 1 method you please. I'm just going to factor it because that's always my first choice. So that's going to give me t equals 0 and 3 over 2, and I need units for both of those, so I'm going to just write seconds, or just s is fine. 7 is asking us over what time intervals is the object moving right, which would mean that the velocity is positive, or left, which would mean that the velocity is negative. So thinking about number 6, what we just figured out is that the 2 times that it's not moving at all are at 0 and 3 over 2 seconds. So really we can just make a sign chart here to figure out what's happening left of 0, in between 0 and 3 over 2, and right of 0. And what I mean by that is you can just think about what happens if you plugged in a negative number into our velocity function from number 3. So in my head, I'm just going to plug in -1. If I plugged in -1, 48 times -1 squared minus 72 times -1, that's going to be a positive number. So I'm just thinking of a number smaller than 0, plugging it in to see what would happen in the velocity function if I did that. I would get a positive number. Something between 0 and 3 over 2, like 1, if I plugged in 1, 48 minus 72 would give me a negative number. And if I plugged in something more than 3 over 2, such as 2, 48 times 4 minus 72 times 2, that's going to be a positive number as well. And you can check that, but that's helping us identify what exactly is happening when our time is less than 0, which that really shouldn't make sense for right now, but we're going to include it anyways. What's happening between 0 and 3 over 2 seconds, and what's happening from 3 over 2 seconds, 1.5 seconds up. And then I would like that final answer to be an interval notation. If you want to write it as an inequality, that's fine. So it's moving left from 0 to 3 over 2, because that's when we have this negative here. It's moving right when it's less than 0, and when it's greater than 3 over 2. 8 is asking us for the total distance, which means we need to think about every place that it's changing between 0 and 2. So I want to look at what's happening for the position at 2. That's our end time. I want to look at what's happening for the position at 0. But I also, in between 2 and 0, there is a point where it's changing direction, and I can see that on number 7. It's changing direction at 3 over 2. So I also wanted to know what's happening, what the position is at 3 over 2. Let's clean that up a little bit. So plugging 0 into the position function, I get 24. Plugging 3 over 2 into the position function, I get -3. And you can check that. Plugging 2 into the position function, I get 8. So thinking about the total distance from 0 to 3 over 2, it has traveled from positive 24 to -3. So thinking about what that means is it's gone 24 spaces, units, what are we saying, feet to the left, and then 3 more feet to the left. So it's actually traveled between 0 and 3 over 2, it's traveled 27 feet. Then between 3 over 2 and 2, it's traveled from -3 to 8. So it's traveled to the right 3 and then 8 more, 3 to get back to 0 and 8 more. So it's traveled to the right 11. So the total distance that is traveled is 38 feet. And that's that 27 plus 11. 9 is asking you, when is the velocity equal to 54 feet per second? So you can just say 54 equals your velocity function and solve there. Again, you're going to get a quadratic. A couple ways you could solve number 9. Obviously, you could use any solving quadratic method that you learned in Algebra 1. Another way to do it is by graphing. On your graphing calculator, you would have your first, you could set y1 equal to 48x squared minus 72x and y2 equal to 54. Then graph it. You're going to have to change your window so that you can see where they intersect. Since y2 is 54, you're probably going to want your y-axis to go all the way up to 58 or so. And then you can use second trace and then go down to intersect, and that'll help you identify where they actually intersect. And it's a quadratic in a line. It should intersect twice. You should know that. You could also, in the same way, graph 48x squared minus 78x minus 54 and figure out where the zeros are. That will give you the same values. You can also use Solver, and Solver is really different depending on how the graphing calculators work. I have one of the older ones. It's not like a digitalized screen, so it's, for whatever reason, I have a lot more trouble working with it. But if you go math and then you scroll all the way down to the B, which says Solver, you can type in your function up top, 48x squared minus 72x minus 54 equals 0. And then if you hit alpha enter, you'll see that solve is what you get when you hit alpha enter. It'll give you one of your values, and then you just have to manipulate in there a little bit to figure out how to get your second. So I'm more comfortable with the graphing features on the graphing calculator, but you could do it that way as well. Either way, your two answers, t is going to be equal to negative 0.549 or 2.049 seconds. So something that I don't think we have talked about yet, you should always have 3 decimal places, either truncated or rounded when you are writing your answers in Calc BC. That's true for the AP test and for every assessment that you take in this class. 3 decimal places. Whether you literally just stop writing after the third number, that's called truncating, or you round appropriately, as you have learned in previous classes. The last question on this slide, number 10, is talking about the total displacement between 0 and 2 seconds. So total displacement is the final position minus the original position. Looking at number 8, the final position is 8. The original position is 24. So the total displacement is negative 16 feet. Whoops. So basically thinking about 8, the total amount that has been traveled was 38 feet. Like if I was driving my car, the total well, not miles, but the total increase on my odometer would be 38. The total displacement, I have all in all, the total overall distance is that I have, in the end, traveled 16 feet to the left. Left because it's negative, and horizontal movement. Okay, these next few examples, the graph at the right is showing the position function of an RC car. So the y-axis is position with respect to time, and the x-axis is time. Answer the questions with a brief explanation. So I'm going to verbally explain more so than writing because I didn't leave myself very much space to do that. But was the car going faster at point A or point B? So that's asking me to look at the slope. Where is there a greater slope, or where is there a greater velocity? So I'm looking for the greater slope or velocity and just thinking about what's happening at the slope of A and at the slope of B. Whoops. B seems to have a greater slope. And remember, the slope is the derivative of position, which is velocity. So greater m, I'm going to say, for slope. Between which 2 points is the car stopped? So we're looking for, if it's stopped, the velocity would be 0. So we're looking for a slope of 0. That looks like it's happening between C and D, and that explanation would be because the slope is 0. 13 says, at which point was the car's velocity the greatest? So the velocity will be the greatest when we have we're looking for the steepest positive slope, which positive because velocity has sign and we are looking at greatest. So the greatest velocity would be at point B, since it looks like A, B, and C are the only points that have a positive slope anyways. And then 14, at which point is the car's speed the greatest? Remember, the speed is the absolute value of velocity, so we're really looking for which point is the steepest or has the steepest slope, and that looks like E. Again, we're drawing generic conclusions since there aren't any numbers on the graph. Okay, we're going to focus just briefly on vertical motion, talking about an object moving up or down, like throwing a ball up into the air. Straight up into the air. So a couple things to note when we're talking about an object being on the ground, that would mean that its position is 0. To find when the object's at its maximum height, that would be when the velocity is 0. Just thinking about throwing a ball up in the air, it's going to stop before it comes back down, so that's why the velocity would be 0. So let's look at this example. We're given a position function in feet for a ball being thrown into the air from the top of a building at t seconds. So finding the initial velocity means that we first need to find the velocity function. So we're going to take the derivative of the position function to get our velocity function, and then initial velocity would be when time is 0. So the initial velocity is 48 feet per second. At what time does the ball hit the ground? That means our position function would be equal to 0, so we're going to set up a quadratic and solve that. I'm going to divide all these terms by -16 in the hopes that that makes it easier to factor, and I can do that since 0 also divides by -16. I'm not even going to show the factoring step here. This factors to be t minus 5, t plus 2, so that would give us 5 and -2 as the options. -2 doesn't make sense here, so the ball hits the ground at 5 seconds. And then 17, at what time does the ball reach its maximum height? So again, we're looking for the velocity function to be equal to 0. So we can set that equal to 0. That's going to give us that t is 48 over 32, which is 3 over 2 seconds, or 1.5 seconds. Okay, the last thing I want to add to today's lesson is just teaching you a little bit about how to use your graphing calculator in terms of derivatives. So I just have a TI-84 Plus. I don't have one of the fancy computerized electronic screens, so some of the stuff might look slightly different, but the basic way to go about doing it is the same depending on what graphing calculator that you have. So if you push Math and you scroll down to the N derivative button, which is also the number 8 on my calculator. So instead of scrolling every time, I actually just hit Math and then I type the number 8 in, and it sounds silly, but it saves you time. And then you can set up to find a derivative. So you're going to see something that looks like this. So you can type d dx, so you're going to type an X or any variable. Nope, X, you're gonna use X. And then this blank right here is where you would type the function in, and then you can evaluate it when X is equal to a particular number. So your graphing calculator won't actually evaluate a derivative and give it to you as a function the way that we normally do by hand. It will evaluate a derivative at a particular value. So it is kind of limited in that way. So you'll notice on both problems 18 and 19, it's asking you to find a derivative of a function we don't know how to find the derivative of yet, but it's asking you to evaluate it at particular values. So go ahead and pause this video. On your calculator, hit math derivative and type in the function and evaluate it at each of those values, and then unpause and see how you did. So d dx of 3 e to the x evaluated when x is natural log of 2 is going to give you 6 point, and then 5 zeros 1. Again, you're always going to have 3 decimal places. You don't have to write this as 6.000, but I really want you to be familiar with the process of writing 3 decimal places, whether truncated or rounded. Then if you're going to do this again, instead of retyping everything, you can actually just scroll up, hit that function, and then where it says natural log of 2, you can just delete that portion and replace that with 3.2, which should give you 73.5976. So you could either write that as 73.597, which is what I'm going to do, because that's truncating, or you could round that up to 73.598. So similarly, I'm hitting math 8 d dx of x to the 1 over x evaluated when x equals 3. That's going to give me negative 0.1058. I'm going to truncate that, so I'm just literally going to stop writing after the 3rd decimal place. You could also round that to negative 0.016. And then I just went up, hit that again so that I could just change the value I'm evaluating it at to be 1/3, and then you get 510.035. Okay, the last thing I'm going to show you or explain to you is how to use your graphing calculator, the graphing portion of it, or the y equals settings, to look at derivatives in different ways. So I know I would love to be able to share my screen with you. I don't actually have that kind of capabilities right now, but you could look up a video on YouTube if you want to see what's happening on the screen. So what I'm going to have you do is go into the y1 feature of your graphing calculator and type this function, natural log of x squared minus 2. Then go down to y2, hit math 8 or math and scroll down to derivative, and then type d dx. And then you could retype the function, but instead of retyping the function, what you can actually do is you can hit alpha trace, and that will pop up a menu that allows you to just simply click on y1. That's going to make your life a lot easier, especially when we're using more complicated functions. And then the other key thing I want you to notice is that you're going to look at what happens when x equals x. Here you're not actually going to make x be a number, you're going to make x be x. That way, if you then graph it, you now have the graph of the original function and you have the graph of the derivative. In a similar manner, you could actually go down to y3 and use the derivative of y2. You could set it up in the exact same way. So then you could also have on your graph the graph of the second derivative, which could be helpful in different ways. So that's just something that could help you look at things. I'm not going to sketch the graph down here. I know that you're totally capable of doing that on your own. The other thing I want to point out is if you hit, while you're in the y equals function, if you hit second table, that'll take you to an x, y1, y2 table, and you could actually evaluate your function or your derivative at multiple values. So remember that when you're doing this, you need to hit second table set and make sure that where it says independent is on ask instead of auto. And then when you're in that table, I could type the number 4, and then I can see that the original function evaluated at 4 is 2.639, but the derivative at 4 is 0.57143. So if I was asking you to evaluate a derivative at 6 or 7 different values, it might be easier, instead of continuously doing it on your calculator, by typing all of that in, to just go into the table feature and spit these x values into that table. So the same process works for 21. You can go ahead and do that, and then you can check your graph on Desmos to make sure that that works out. So hopefully through this lesson you have an idea of the relationship between position, acceleration, and velocity. And you know the difference between speed and velocity. You know about displacement versus total distance. and about vertical motion. And then really focusing on, can you use your graphing calculator to help you with more complex derivatives? Because as of right now, we don't know that many derivative rules other than the power rule that are going to help us simplify things. So a more complicated derivative you would only be able to do using a calculator. So you need to know how to use your calculator to calculate derivatives at particular values, to graph them, and so forth. So I hope you found this video helpful.